All right, let's talk a little about acids and bases. Now, one of the reaction types that we looked at was a special case of the double displacement reaction, was an acid-base reaction in which the acid and the base neutralize each other. So let's look at definitions of acids and bases. There are three sets of definitions that are widely recognized in chemistry. The first is the Arrhenius definition. And here's just a quick Googling and a Wikipedia article. I know Wikipedia is not considered a good source, but it's fine for what we're doing here. I just want you to see who this guy is. Swedish chemist, born in 1859, died in 1927. He was one of the founders of physical chemistry. So he lends his name to this definition of acids and bases. Now, by the Arrhenius definition, an acid is a substance that when it's dissolved in water, it produces what are referred to as hydrogen ions. That's hydrogen atoms that have lost their only electron, leaving them with a positive charge. Remember, a hydrogen atom has one proton, one electron. Yes, there are three isotopes, and they may or may not have neutrons, but that's not what we're looking at right here. We're considering that the hydrogen has lost its electron, and that makes it be a hydrogen ion. Now, by the Arrhenius definition, a base is something that when dissolved in water produces, here's one of those polyatomic ions you need to know, hydroxide, OH negative. All right. The second set of definitions are attributed to two people. Let me see if I can't find a little info for you on those people. So the Bronsted-Lowry theory, here you go. You have Bronsted. I'm not up on my Danish, and I'm not sure the little hack mark through the O there. I'm not sure what that does to the pronunciation. I think it might make it more of a Brunstead, but I'm not sure. Anyway, so Bronsted and Lowry, who was an English physical chemist. So what did they have to say about acids and bases? Well, by their definition, an acid is simply referred to as a proton donor. A donor is one who donates. Okay, so an acid will donate a proton. Well, that's really saying pretty much the same thing as Arrhenius, just in different terms. Again, if you consider a hydrogen atom to be one proton orbited by one electron, and if you lose that electron to gain the positive charge, then all that's really left here in a hydrogen ion is the proton. So if the acid gives off a hydrogen ion, it has given off or donated a proton. But where their definition gets a little easier to work with is that they refer to bases as proton acceptors, or as Mr. Spock would have said on Star Trek, acceptor. This is a little more in line with the definition you find in a lot of biology textbooks, where they simply say that bases combine with the hydrogen ions or the protons that acids give off. All right, a third definition comes to us courtesy of the great American chemist Gilbert Newton Lewis. And let me see what we can find about Gilbert N. Lewis. Here he is. Here's the Wikipedia article. Here's what he looks like. He's an American physical chemist. You know him because of Lewis dot structures. Electron dot diagrams is what they're called sometimes. So now Lewis was all about the electrons and pairs of electrons. So he described an acid as something that will accept a pair of electrons. Electron pair acceptor. And a base is an electron pair donor. So for a good example here, let me see, I'm getting a phone call. I'll be right back. Okay, so here are our three sets of definitions. Arrhenius, Bronsted, Lowry, Lewis for acids and for bases. Now let's look at some examples. HCl. Something I think I failed to mention about this earlier. Couple of options here. If you see this in the gas state, then the most appropriate name for this gas would be hydrogen chloride. Hydrogen chloride. But we will normally not deal with this as a gas. We will see this in an aqueous solution, in which case we would name it the way our nomenclature flowchart tells us to name it, which is hydrochloric acid. Okay, hydrochloric acid. Now, what this will do in water is it will separate the pair of electrons that was being shared between the hydrogen and the chlorine. The hydrogen's going to turn to chlorine and say, look, I'm leaving, you keep my electron. So when hydrogen separates from chlorine and leaves its one and only electron behind, the hydrogen becomes positively charged. Chlorine keeps hydrogen's electron, which looks like an extra electron for chlorine, giving it a negative charge. So hydrogen chloride gas, when dissolved in water, separates into hydrogen ions and chloride ions. So it dissolved in water and it produced a hydrogen ion. So it's an acid by the Arrhenius way of thinking. In the Bronsted-Lowry way of thinking, it donated a proton. This hydrogen ion is a proton. From the Lewis perspective, that proton would be happy to accept a pair of electrons because this hydrogen ion has 0 electrons, but a pair of electrons would not only replace the one that it gave up, but it would fill its first shell, and that would make the hydrogen happy. Now let's consider hydroxide. Well, let's think about, let's look at this. Sodium hydroxide. Now, technically this is a salt, and we haven't talked yet about salts. But it has a metal ion, sodium, which is positive, together with the polyatomic ion, hydroxide, which altogether is negative. So when this is dissolved in water, the two ions simply separate, and that means it gives off, it produces hydroxide. Now, That makes it a base. Now, from the Bronsted-Lowry perspective, the hydroxide would gladly accept a proton. In other words, this hydrogen ion, this proton, coming from hydrogen chloride or hydrochloric acid, could join up with this hydroxide. So if we take a positive hydrogen and a negative hydroxide and put them together, what do we get? We get water. The base, which is the hydroxide, accepted the proton, which was donated from the acid, and we got water. Okay? Now let's consider ammonia. Ammonia is NH3. As far as a Lewis structure for ammonia, it has 5 valence electrons, and there are 3 hydrogens bonded to that with covalent bonds, and there is an unshared pair of electrons on the nitrogen, or a lone pair. Now, if the only definition you knew was the Arrhenius definition, and someone said, based on that, an acid will give off H+, and a base will give off OH-, hydroxide, what do you think ammonia is? A lot of people would say, well, it has to be an acid because it's got hydrogens, so it can give off positive hydrogens, and it doesn't have any oxygen, so it can't be a base because it can't give off OH. There's no oxygen in it. Well, here's where knowing all 3 of these definitions comes in handy. What you have to consider is that for the Arrhenius definition, they said that a base will produce hydroxide when it's dissolved in water. So we need some water here. So let me draw water with a different color. If we draw water this way, oxygen has 6 valence electrons. There they are. Hydrogen has 1. We'll put another hydrogen down here with 1. So here we have water. So what happens is that this is going to be able to share this, or donate, would be the better word, this pair of electrons. It can be an electron pair donor, which means it can be a base in the Lewis sense. So what does that mean will happen? Water will act like an acid. We're going to take this hydrogen off, just like we broke the hydrogen loose from the chlorine up here. And the hydrogen says to the oxygen, you keep my electron. Now that's this electron here. Okay? So the hydrogen says to the oxygen, I'm leaving, you keep my electron. So this hydrogen leaves with a positive charge. Now, what would this proton that was donated from water be happy to do? It would be happy to accept a pair of electrons, this pair of electrons. So the NH3 is going to accept the proton. This hydrogen is going to move over here and bond on these 2 electrons. That's something we call a coordinate covalent bond. So now the hydrogen moves over here, and instead of NH3, we'll have a 4th hydrogen. We'll have NH4 with a positive charge, one of our polyatomic ions called ammonium. But on the right side of this squiggly line, we have an O and an H, and that electron right there that used to belong to this hydrogen but was given to the oxygen gives this a negative charge. And what is OH with an extra electron and therefore a negative charge? It's hydroxide. So when we put the ammonia and dissolved it in water, a proton is transferred from water to the ammonia, turning it into ammonium and creating hydroxide. So we satisfied the Arrhenius definition by producing hydroxide when we dissolve the ammonia in water. The ammonia acted as a proton acceptor. It accepted the proton that came from the water. The ammonia donated the pair of electrons. So in all three definitions here, ammonia is a base. Water here acted as the acid. It produced a hydrogen ion, although it didn't have to be dissolved in itself. It donated the proton, and that proton accepted this pair of electrons. All right, so we will work with these more, and all of these things will just keep coming back up, and that will give you more and more opportunities to develop an understanding.